right, we are continuing on with our Unit 8, still Target 1 here, still looking at these polar equations, these polar graphs here that were kind of started earlier this week here. So earlier this week, we were graphing things that were mostly circles. Today's are not circles, but you'll see a lot of the same patterns that we see when we graph the circles. You'll see that they kind of look like it, but they're kind of unique looking. So what I actually want you to start with is in just a second here, I want you to actually pause the video and I want you to just kind of play around with this. If we were in class, I would give you a few minutes with your group and you would just sort of play around with some of these equations. These are just some examples. Try your own. Figure out some other ones. Notice all of these though are still R equals. So R equals and notice you have an a value in front right here, so an a value times either the cosine or the sine, and then we also have a k value afterwards as well. Notice that there's no b value, no h value here. We're just focusing on the a and k. So play around with them a little bit. These are some examples. You can either do it on your calculator or you can actually do it on Desmos as well. Just to show you something on Desmos here, you'll see I have one of them graphed here. This is one of our kind of fun looking graphs. If you're going to graph it on Desmos, when you go to that website, go to the little wrench over in the corner here, and that's our graph settings. Normally we are on rectangular grid here. That's our rectangular normal Cartesian coordinate, and this is the polar graph here. So click on that one, that kind of circle one, and that will change it. Make sure you're in radian mode. And then what you want to look at when you're actually typing in the equation, you're going to need a theta value, so r equals in the theta. Usually what I actually do is just type in the word theta, and Desmos will change it into the symbol theta. Another way that you can do it if you don't like doing it that way, sorry, didn't mean to hit that one, this keyboard right here, this keyboard here, and then go away worksheet, sorry. If we're looking at this one, we're going to go to that ABC, and then here's our theta value right there. So again, usually I actually just like to type in theta, but that's one way you can kind of explore it. So pause the video right now. These are just some examples. Try them, kind of take a look at the patterns and see what they look like. All right, hopefully you did play around with them a little bit here. So this is a class of polar equations that we call limacons. Kind of a weird word, but it's called a limacon. And we have four basic shapes. Now, I don't really need you to know the actual names of all of them. There's a cardioid, a dimpled limacon, a convex limacon, and limacons with an inner loop on that here. So if you graphed those, if you graphed the ones up above, you graphed at least one of each. We'll start with the cardioid here. And I started filling this out just to make it a little bit quicker to go through here. Let's start with the cardioid. And the first thing I want to look at, though, before I even graph that one specifically, if you look at the two that are the sine, take a look at what's in common with those. So this one was a sine and this one was a sine. Notice that those are both symmetrical with the vertical axis. Notice that the cosine ones are symmetric to the horizontal axis. If you look at the sine ones, again, those are both symmetric to the vertical. If I look at the cosine, those are both symmetric to the horizontal. If you think back to earlier this week when we did our circles, it was the same thing. All of the cosine circles were symmetric to the horizontal axis, and all of the sine circles were symmetric to the vertical axis there. So that's something to always kind of keep in mind. So if I'm looking at this one, this is what we call a cardioid. Again, I kind of think about cardioid, sounds like we're thinking of maybe like a heart. Notice it kind of does look like a heart kind of shape right there. So that's our cardioid. And again, a couple questions I asked you here. Greatest distance from the pole and shortest distance from the pole. So greatest distance from the pole is 4 units away from the pole. Shortest distance is 0. Kind of think about why that makes sense. Again, we talked about it earlier this week. What's the greatest value for the sine? We know the biggest value for the sine is 1. So 2 times 1 would give us 2, plus 2 would give us 4. So our biggest distance from the pole is 4 units away. Shortest distance from the pole, again, if you think about the smallest value of the sine that's possible, smallest value would be -1. So 2 times -1 would be negative 2. Negative 2 plus 2 gives us 0. That's our shortest distance from the pole. So that means that it actually does intersect the pole. And you can see that from our graph that it does intersect the pole. Now you'll notice, kind of looking ahead, that I have one other graph that it says it intersects the pole twice. So one of the things that I want to think about is how do we know which it would, how many times it would intersect and where does it intersect? I left that one blank here. Really, to answer those two questions, you're thinking about where does r equal 0, because it would intersect the pole where that r value, or the distance away from the pole, is 0. So if I think about this first one, if I do 0 equals 2 times the sine of theta plus 2, subtract the 2 and divide by 2, we would get negative 1 is equal to the sine of theta. So we would want to think, all right, where does the sine equal negative 1? And the sine equals negative 1 at 3 pi over 2. So it actually only intersects the pole at one spot where that r is equal to 0 at 3 pi over 2. Taking a look at the next one here. So the next one is our dimpled limacon. Okay, here's another cosine, or here is a cosine one. Again, it's symmetric to our horizontal axis right here. Thinking about the greatest distance from the pole, notice this greatest distance is 8 away from the pole. But notice it doesn't go through the pole. This is what we call like our dimple over here. If you kind of see it, it goes out and comes back in, just like a little dimple on that there. So notice it doesn't go through the pole on this one. So our shortest distance from the pole is actually 2. Again, think about why this might make sense. What's the biggest value that we can have for the cosine? We know that's 1. So 3 times 1 would give us 3, plus 5 would give us 8. Okay. And what's the smallest distance we have for the cosine? That would be negative 1. So 3 times negative 1 is negative 3, plus 5 is 2. So that's what we're thinking about. Greatest distance from the pole, smallest distance from the pole. Now, you can see from the graph here that it doesn't intersect the pole at all. So here we don't have a spot where it intersects the pole. But if you didn't have the graph, how would you know that? Again, think about if you were to put 0 in for r. So I'll do it right here. If I put 0 in for r, theta plus 5, if I subtracted 5 and divided by 3, we would want to solve where the cosine is equal to negative 5/3. Again, we hopefully remember from our last unit that can't happen. The range of the cosine is only from negative 1 to positive 1. Negative 5/3 is smaller, so there's no solution to this actual equation. So that tells us that there is no place where the r value is 0, so it doesn't intersect the pole at all. Okay, so that one again is called our dimpled limacon. The next one you'll see is kind of similar. This one's a sine. Let's look at this one here. This one is called our convex limacon. If you notice, kind of similar to the dimpled one, but if you see it, it's kind of flat right here. So this one, again, called our convex limacon. Again, I don't really care that much about the words, but just so you kind of get an idea of what it looks like here. So notice, again, symmetric to the vertical axis like our normal sine circles were before as well. So this one, greatest distance from the pole is 6, smallest distance from the pole is 2. Notice it does not cross through the pole at all. So let's go back and look at it. Again, thinking through it, too many things open here. The biggest value for the sine would be 1. 2 times 1 plus 4 would give us 6. Smallest value for the sine would be negative 1. 2 times negative 1 is negative 2, plus 4 gives us 2. So that's we can figure out our greatest distance and shortest distance there. And once again, we know it does not intersect the pole. If I put in 0, I'll just do it over off to the side here. We would get negative 2 is equal to the sine, and again, there would be no solution for that one, because again, it cannot be smaller than negative 1 there. So it does not intersect the pole at all. All right, last one to look at is our limacon with an inner loop, and I think this one kind of looks the coolest. If we look, that's what this one looks like. Hopefully, again, you played with some of them and kind of saw these here. So this one is like a loop within a loop here. So here, our greatest distance from the pole is 3 units away. And our shortest distance from the pole, careful, we're not looking at this one right here. It does cross through the pole. So our shortest distance from the pole is 0 on this one here. But, okay, we look at it here. So greatest distance is 3, smallest distance is 0. But notice it does cross through the pole, but I said it crosses twice. Think about this here. If I were to put, kind of squeeze this in here, if I were to put 0 in for r, we would have, or we would want to find where is the cosine equal to -1/2 here. So there are two places where the cosine is equal to -1/2, at 2 pi over 3 and at 4 pi over 3. So what actually happens here at 2 pi over 3, it is like, so it starts, here and kind of swirls around on that. It crosses through and then it crosses through a second time. And I'll show you that when we actually go through and kind of look at the graph on those there. So those are our 4 different types. So let's look at how we actually go through and graph these here. So looking at this first one, really what I like to start with is I like to start putting, I'll say with r equals 0. I like to put r equals 0 in first. Really what that tells us, again, is how many times it intersects the pole, and that can kind of give us an idea of what our graph kind of looks like here. So if I solve this, I would subtract the 2 and divide by -4, so I would get 1/2 is equal to the cosine of theta. So where is the cosine equal to 1/2? We know that excuse me, is at pi over 3 and at 5 pi over 3. So what that tells us, if it crosses through twice, that's going to compare to that limacon with the inner loop on that. So we're going to have an inner loop. So just if I start looking at the graph of it here, I can think about, all right, we know it is going to cross through the pole, and it's actually going to cross through the pole twice. So I like to go through and think about what we did the other day when we were graphing our circles. Let's think about the theta values at 0, at pi over 2, at pi, and 3 pi over 2, sorry. So I'm going to actually make a little table for us just so we know where our numbers are coming from. Sometimes it gets a little overwhelming on these. So I'm going to do 0, pi over 2, pi, and 3 pi over 2. So if I put in 0, so the cosine of 0 we know is 1. And so then I'm going to do -4 times 1 is -4 plus 2, I get -2. So at 0, we're going to go in the -2 direction. Remember, positive would be over here along with 0. Negative would be in that other direction. So that's our -2. At pi over 2, we know the cosine of pi over 2. Sorry, again, too much open here. Go away. Sorry, guys. Wrong one. There we are. Cosine of pi over 2 is 0. -4 times 0 plus 2, we're going to get 2. So at pi over 2, it's going to be up here at 2. So it looks kind of weird right now. At pi, we know the cosine of pi is -1. So -4 times -1 is +4. 4 plus 2 gives us 6. Notice that's going to be our furthest point away over here. And then at 3 pi over 2, we know cosine of 3 pi over 2 is 0 times -4 is 0 plus 2 is 2. So we have another point here. Now, you can kind of tell a little bit of what this is going to be. Again, we said because it intersects twice, that's going to be an limacon with the inner loop. So we know there's going to be that loop that goes about right here, right? And then we know it's going to curve around. Now, what we like to do is we like to come up with at least a couple more points here to help make it a little better of a shape here, kind of a little more of a circular shape. So we want to come up with some other nice and easy points that we could do. So if you want to think about it, we could try and think where is, we usually like the 1/2. So we did that the other day as well. Where is the cosine 1/2? So the cosine is 1/2 at pi over 3 and 5 pi over 3. Now I'm not going to use positive 1/2 here because we know that gave us 0. So that's not going to help us on this one as much. And another way to think about it is most of our graph is in the negative side over here if you think about this going in the left-hand direction. So I'm going to think, all right, let's maybe think where the cosine is negative 1/2. So we know the cosine is negative 1/2 at 2 pi over 3 and at 4 pi over 3. So again, we're using those. You could technically really use any numbers along the way. Just the 1/2s and negative 1/2s. Those are just nice, easy numbers to work with. So cosine of 2 pi over 3 would be negative 1/2. Negative 1/2 times negative 4 is 2, plus 2 is 4. And then we know it's going to be the same at this one. Again, it was negative 1/2, and that would give us 4. So at 2 pi over 3, we're out here 1, 2, 3, 4 away. And then at 4 pi over 3, it's 1, 2, 3, 4 away as well. So if we're thinking about the graph of this one here, again, it actually started at negative 2. It comes around, loops around here. Again, that other value helps get kind of a nice circular part on here. Loops back, comes back at 0, and finishes that inside loop. This should maybe a little more circular right here. And this is what our limacon with the inner loop ends up looking like here. So let's try another one. If I look at this one here, so again, I'm going to set where r is equal to 0. So 0 is negative 3 times the sine of theta plus 3. Subtract the 3, divide by negative 3, we get 1 is equal to the sine of theta. So that means theta is equal to pi over 2. So that way, that kind of tells us at least that it is going to cross through the pole. So we do have a point right here at the pole. It's really at pi over 2 and then at 0 there. And we know then if it only crosses through once, that's going to correspond to that cardioid. Okay, so if I look at this here, let's come up with some other values. So r and theta. Again, the reason we like to do that r equals 0 first is it just kind of helps us gives us kind of an idea of what this graph might look like here. So again, I'm going to do 0, pi over 2, pi, and 3 pi over 2. I already did pi over 2. We know it's going to be 0. Okay, we don't even need to redo that one. If I think about this, the sine of 0 is 0. 0 plus 3 would give us 3. So we have a point right here. Okay, and then keep going. Sine of pi is 0, and then 0 plus 3 would give us 3 again. So at pi, we're going to be over here at 3. Sine of 3 pi over 2 we know is negative 1. Negative 1 times negative 3 is positive 3, plus 3 is 6. That's going to be our furthest distance away here then. So again, you can kind of start to see it take a little bit of shape here. And again, we know it's going to be a cardioid, so it's going to come back around here. Like we said before, let's come up with some other values to help us out here. So let's pick up where it's either positive 1/2 or negative 1/2. Now, I kind of like to look, maybe I'll think about the negatives just because I'm kind of going in that bottom direction right here. I'll actually maybe do the positives as well, just to kind of take a look. But if I did, again, where is the sign negative 1/2? That's going to be at 7 pi over 6 and at 11 pi over 6. So if I did negative 1/2, negative 3 times negative 1/2 is 1/2, plus 3 gives us 4/2. Again, that would be the same value right here. So we can graph that. So we're 1, 2, 3, 4.5, and 1, 2, 3, 4.5. Again, you can tell that that can kind of help us make our cardioid look a little bit better. You wouldn't have to, but you could do 11 pi, or I'm sorry, 1 pi over 6 and 5 pi over 6. Again, we know that the sign of pi over 6 is positive 1/2. So negative 3 times positive 1/2 would be negative 1.5, plus 3 would be 1.5. It's going to be the same values here. Again, the reason I picked the other ones is just I knew that would help me make this bigger curve shape a little bit better. But if you really wanted a nice cardioid, And you kind of see that'd be 1.5 right here. That can kind of help you form those. So this cardioid, I can draw it in here nice, looks, that should be curving right here like this. Okay, let's do one more and just take a look at what it looks like here. Again, I am going to start off and let's put where r is 0. So what we're going to get if I subtract the 4 and divide by 2, we want to know where is the cosine -2. It is not. There is no solution to that. So that means it does not intersect the pole. Okay, so that tells us that it's going to look like one of our other two, either the dimpled limacon or the convex limacon. And so let's graph it and just to kind of take a look at what it does look like here. So I'm going to think through my theta values that are nice and easy to go through. So we're going to start with the 0, pi over 2, pi, and 3 pi over 2. Keeping in mind that it's not going to actually cross through the pole here. So if I put in 0, cosine of 0 is 1. 2 times 1 plus 4 gives us 6. So we're starting off with a point over here. If I put in pi over 2, cosine of pi over 2 is 0. 2 times 0 plus 4 is 4. So we have a point up here. And then cosine of pi is -1. 2 times -1 is -2. Plus 4 gives us 2. So we're here. And then 3 pi over 2, cosine 3 pi over 2 is -1. I'm sorry, is 0. Sorry, is 0. 2 times 0 plus 4 gives us 4. Again, 1, 2, 3, 4. Notice that it's a cosine 1, so it's going to be symmetric to our horizontal axis here, and you can kind of see it taking a little bit of shape that, it's going to be the bigger area out here, maybe dimpled or kind of flat over here. So let's come up with at least a couple more values that might help us here. So this one, again, since most of my graph is over here to the right, I'm going to think about maybe my positive ones, maybe my pi over 3 and my 5 pi over 3. Again, those are the values where cosine is 1/2. So that's why I'm choosing those, just because they're nice, easy values. So I'm going to do pi over 3 and 5 pi over 3. So 2 times 1/2 is 1 plus 4 would give us 5. It would be the same here. So 1, 2, 3, 4, 5. And 5 would be right here. Again, it's symmetric right there. If you wanted to, you could also do the 2 pi over 3 and 4 pi over 3. I like to sometimes do those, both of them in there, because it really gives you a nice shape to your graph. Because so and it's not, doesn't really take that much longer. Cosine of 2 pi over 3 is -1. So 2 times -1 is -2. I'm sorry, was -1/2. Wow. Cosine of 2 pi over 3 is -1/2. Times 2 is -1, plus 4 gives us 3. Talking too fast here. And then it would be the same for this one. So at 4 pi over 3, we're here at 3. And then 2 pi over 3, we're here at 3 as well. So you can kind of see the general shape of this one here. That should be a little bit more of a curve. It's hard to draw on the computer here. And it kind of comes in just that little bit right here and has that little bit of that kind of flat or dimpled side to it right there. Okay, so try these on your own. You have a few of them on your homework for today. You'll also kind of notice a little bit with the homework that there are some review problems on there as well. So you'll see some that have that A and K value. If it doesn't have all of those values in there, again, it might be like a little bit different. You'll kind of take a look and see what it looks like along the way. Like the ones that we graphed the other day didn't have an A and a K value. It just had an A value. So kind of pay attention to that and try these. And again, let me know if there are any questions. Thanks, guys. Bye.